Hello there. Today we're going to talk about how chemical structures can relate to their properties. So things that actually make the structure or the molecule do what we expect it to do as related to its chemistry. All right. So let's think about some things that we already know. So consider the properties of these substances based on what you already know. How do they look like, feel like, interact with other things? What are they used for? Where do you find them? So these are mostly pretty easy things. Oil, we know what oil is, like the kind of olive oil that you might use in your cooking. It is a liquid, but it does not mix with water, which is the thing that makes stuff wet. So both of those are liquids, but they're different liquids because they do not mix together. You can heat oil a lot higher than you can heat water because water will evaporate, and oil doesn't really do that. It gets warmer. You can freeze water, but you can't freeze oil, or at least not at temperatures that you would normally interact with, and not even at upstate New York temperatures, which is what I live in. So both of those are things we can ingest, although they definitely do different things for us. If you're ingesting oil, it is probably being used as an energy source. If you're ingesting water, it is liquid. We use it for lots of things in the body. And then salt is the only solid on this list. It is not just a solid, it is a crystal solid, and it falls apart easily. So if you've ever had a large chunk of salt and you kind of hit it, it falls apart. The salt does mix with the water. I would not say it mixes as well with the oil. I mean, it'll like sit in it, but it won't come apart or change structures in it. So oil, water, and salt. We know a little bit about those. Okay. This is the structure of oil. So what do we notice about the structure of oil? I think it's important to see what we can figure out. Well, we can see what it's made of. In biology, these long strands here are all carbons. So carbon, 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 carbon. It's pretty much like having a C on each of these little pieces. And in fact, all of the C's are also connected to H's. So the C also would have an H connected to it. And since carbons connect to 4 things, it's connected to a carbon here and a carbon here. It would have at least one more H connected to it. Over here, this C is actually connected to twice to the C next to it and one other carbon. So it only has one H. This appears to be an unsaturated oil because saturated would mean that it has none of these double bonds. And in this case, it is see how multiple strands are unsaturated? So a polyunsaturated fatty acid, which makes sense for soybean oil. So PUFA, by the way, if you've never heard that before, polyunsaturated fatty acid. The other thing that these have are some oxygens, but not very many. So most of it is these long strands of carbons. This is what oil looks like, and a couple of oxygens. It's a fairly large molecule, and it's real long. All right. Here's the other 2 of our molecules, which is water over here. You might recognize it, H2O, and salt. Now, they both look fairly different from the oil, first of all. They're smaller in terms of the number of things. These 2, the sodium and the chloride, are both much larger than the oxygen and the hydrogen. So salt's still bigger than water, but both smaller than oil. Also, they've got some different stuff. For instance, there are no carbons in either of these, which is kind of interesting. So these 2 things mix together, but not with this one. And this one has mostly carbons, and these 2 have no carbons. Mostly carbons, no carbons. I wonder if the carbons are what's related to the things not mixing together. You'll also notice that this here is a little bit off balance. These little dots, they stand for electrons. So even though these electrons are not specifically somewhere else, like there's a balance of electrons and protons in this molecule, there's still electrons kind of hanging out on their own. Over here, we see something different. We see a plus with the sodium and a minus with the chloride. Now, the minus suggests, again, an electron, only in this case, it suggests one that's off balance. So there must have been one that traveled from the sodium to the chloride. So there's a free electron hanging out here that's not usually there. So both of these have electrons that are kind of available and in ways that are not obviously connected to anything else. I wonder if that also relates to how they interact with each other. So now we're starting to get a sense of how these different structures work. The other thing that's different about some of these, so over here, these are all connected to each other, lots and lots of lines. Over here, the water has lines. The salt doesn't have any lines. That's because these two pieces aren't actually connected to each other. They're just kind of, this one's a plus, this one's a minus, so they attract each other. So that's a little bit different as well. Remember we said that salt kind of falls apart. And so that is a little bit related, getting the idea of how these structures connect. So just to bring this to things you might have already heard of, this is covalent bonds, and these are what we call non-polar covalent bonds. So non-polar covalent bonds is the carbons and the hydrogens. It means that they are balanced, and so that's what gives oil its sort of look. Now that's different from, we move forward in the slideshow, our water, which is actually an off balance or polar covalent bond. So this is a polar covalent bond. Because this one's off balance and the previous one is balanced, they don't mix together. The balanced one and the off balance one, bump, run into each other, cannot stick. The salt is an ionic bond because these are both ions. Because of that, they are also off balance. And off balance things can connect, which is why salt can go into water. So we're starting to see already with just basics how structure works. So I know if I'm looking for something that is nonpolar or like oil, I want lots of carbon-hydrogen bonds. If I want it to be like water, I might be looking for this sort of off-balanced look and maybe these oxygens. And if I want an ionic, I'm looking for pluses and minuses. All right, so let's move forward to some other molecules. Here are two very different molecules. Let's examine them without knowing anything about what they are. So if we start with this molecule at the top here, we still see carbons, because again, connection. But I don't just see carbons. I see oxygen here. I see oxygens coming off of all of these carbons, except this one. This carbon is connected to that carbon, then to an oxygen. But it's connected to an oxygen over here. So same thing there. And there's an oxygen between the two. So this structure has a lot of oxygens. Now, this structure does have loops, just like this one does. This one has them in 5s. This one has 3 loops that are in 6s and 1 in a 5. But I don't see nearly as many oxygens. In fact, all of this is carbon, hydrogen, and hydrogen. Oh, there's a double bond. 1 oxygen, 1 off to the side. So now if I back relate these to what I learned before, this one, having lots of oxygens, feels like it would throw things off balance. So that would be more like water. This one definitely has, even though it's got rings, mostly carbons and hydrogens, so it should be more like oil. Let's see if that's going to be true. All right, but first let's think about some molecules you might know. Sucrose and cholesterol. I definitely know these things. Sucrose is a sugar. It dissolves in water. It is sweet. It gets used for energy. So those are things I know about sucrose. Cholesterol is a fat. It does not dissolve in water. Cholesterol, like in eggs. You ever try to get eggs to mix in water? You gotta beat them pretty hard. It is not sweet. It is definitely savory, maybe even umami, which is that like real savory flavor. And cholesterol. I don't believe I tend to use cholesterol for energy, but I know that it is used to build things. So makes hormones and other structures. So they're pretty different from each other. And if I think about even just these things, it might be similar to the stuff we saw earlier. I might expect this being a fat to again have that carbon-hydrogen structure, this being a sugar that dissolves in water, to either be like the salt or like the water. All right, so let's see what direction this ends up going. Hey, it turns out this one here is the sucrose, so this molecule at the top, and it is indeed lots of oxygens like water, so it would dissolve in water. And this here is the cholesterol. You can see again lots of carbons and hydrogens. So we're starting to get the idea of how structures relate to properties, which is important because we don't know how to get to biology if we can't relate structures and properties. All right, now let's go a slightly different direction. We're going to talk a little bit about water, just the structure of water and how it might work with some other things. Okay. There are too many fruit flies flying around my house. I'd like to catch and kill them. So my first plan was put out a cup of sugar water because they liked sugar. However, they landed on the water and it didn't help because they flew away again. How come they were able to land and then take off? Now, we're probably familiar with this. Insects can land on water and then go away. Why would that be? What is it about water that puts them in the situation of being able to land and then take off again? Well, we already know the structure of water. It's that oxygen with some hydrogens. And obviously, there's usually more than one molecule in a container, so there might be more oxygens and more hydrogens. I'm not going to use the text for this, so you're going to have to deal with my poorly drawn O's. And what is it about these? Now, we said that they are off balance, and that's true. And in the previous image, we noticed that there were some electrons hanging out around the oxygen. Not enough to make it like negative, like part of the salt, but it is enough to make it a little bit negative. So that part's a little bit negative. So if the oxygen's a little bit negative, hey, guess what the hydrogen is? You bet it. It's a little bit positive. So it's a little different. So the hydrogens are a little bit positive. And remember, magnetically, things often connect to each other. So this positive might kind of connect to this negative, making a little bit of a network. So what about the molecules all across the top of my sugar water? And especially if the sugar also can connect and network with the molecules, yeah, it creates a little bit of a net. It's not a very tight one. They're not very strong bonds, but flies aren't very big, especially fruit flies. They're very tiny. So the fruit flies sit right on top of the sugar water because they can catch those little connections, those intermolecular forces. Intermolecular force, which we like to call a hydrogen bond. It's not a bond, it's a force. Also, it doesn't have to be hydrogen, and not every hydrogen does this. So it's poorly named, but that's what it does. So it makes all of these cute little connections. The fly can sit on it, eat some sugar, and run away again. That does not help me. I want to kill the flies. So I want them to fall into the water. So I need to disrupt this network. Hey, is there something that if you kind of mix it in water, it makes the water move or fall apart or scatter? I mean, obviously an oil might do that. But you know what else will do that? Soap. A tiny drop of soap added to the water disrupts these connections in this network. The fly can't tell because it doesn't know you added soap to the water, so it lands on the water with a little bit of soap, and instead of landing and getting nice sugar, falls in and dies. So if you're trying to get rid of fruit flies, I highly recommend it. Okay. What's the next thing about water? I want to find just the right location for growing wine grapes. Wine grapes are very finicky, and if they either get too warm or too cold, they do not survive. They don't make good wines. So I know people grow grapes here in the central to western parts of New York. My favorite Rieslings come from here, but also near the coastlines, like in California. So what water-related phenomena occurs both near Great Lakes and oceans, or big bodies of water, as it might be. Now, some of you may have grown up here near Great Lakes. I grew up near an ocean on the other side of the country in New Jersey, so not California, but nonetheless, here's what I learned about going to the beach. The beach was always 10 degrees colder in the summer, 10 degrees warmer in the winter. How come? I wonder what that could be all about. Well, it must again relate to water. And if everything's going to relate to water, it probably also relates to how these water molecules connect to each other. So, if these water molecules are forming networks, that means that they are making bonds. Bonds, like these ones between the hydrogens and the oxygens, have energy, which I'm going to make a lightning bolt for energy. It's a bad lightning bolt, but you kind of get it. So that's one of my better lightning bolts. Has energy, which actually means that they kind of relate to the weather around them in a whole different way. So water, because it has all of these funny little bonds and things like that, takes a very, very long time to warm up and a very, very long time to cool down. So let's think about this in terms of lakes you might have encountered. If you go to Lake Ontario, for example, in the early parts of summer, it might be very warm. For instance, in June in New York, Lake Ontario, very cold because it was cold all winter and it takes so much more energy to heat it up and make it warmer. But if you go in September, it might still be warm even though the temperature outside is starting to get cold because it takes so long to cool down. Hey, does that help me with the grapes? They don't want to be too warm. They don't want to be too cold. If I put them on the edge of a big body of water, guess what? It helps to temper it. The big body of water stays warm as it gets cold, therefore trying to keep my grapes from completely freezing because it keeps the warmth around it. And I mean, it's not perfect. You don't have to be in the water. This is large scale stuff. And the same in the summer, it keeps them a little bit cooler because it takes a long time to warm up. So there we go. That's how water and all those little connections in water helps with that. Couple more water things. Let's say I'm a fisherman in upstate New York. I'm concerned it gets too cold for the fish in the streams. Wouldn't they freeze each year? If you're a very, very small stream, maybe, but as you probably know, that's not usually what happens up here. I mean, things do freeze over, but they don't freeze solid. How come? So it says, I notice most of the time when something turns solid, it also becomes heavier and sinks to the bottom. Does that happen with ice? Well, does it? If I have a glass of water and, here's my glass of water. I'm going to fill it up with some blue water. My art on here is always fantastic. And then I'm going to add some ice cubes to it. The ice cubes, do they fall to the bottom? Or do they hang out up here at the top? I should make those thicker. They'll look nicer. Yeah. You and I both know that they're going to float mostly to the top. So that means there must be something interesting about water when it freezes that causes it to float to the top. Hey, guess what that's related to? Yep, you guessed it. Those little intermolecular forces that we call hydrogen bonds, because I have my water molecule. I have my other water molecule. And when they're liquid, they make connections to each other, but they can kind of slide around because liquid molecules slide around. But when they start to get solid, those connections actually firm up and make a crystal. When they make a crystal, they actually pull apart a little bit, put space between them, and make this really neat structure that allows it to not get denser because they don't come together, but to pull apart and float. That means the water on the bottom, interestingly enough, is actually warmer than the ice on the top. So what happens if it keeps getting cold? So if I have a stream, let me draw a stream. Here's my stream bed. I'm looking at it from the side. And I've got my water in the stream bed. So I'll draw some water in this stream bed. And it's flowing. And the top of the water gets cold. And it's going to get cold enough eventually to freeze. But before it gets cold enough to freeze, it goes through a couple of different stages where it gets colder, colder, and colder. And this is actually right before it freezes when the water actually gets really dense. So at about 4 degrees Fahrenheit or Celsius, which is a little bit above freezing, so we're talking about 30 something degrees Fahrenheit, about 4 degrees Celsius. The water is as dense as it gets, and it actually falls to the bottom. So the bottom of the stream is 4 degrees. Now that's not enough to freeze. You need to be at 0 degrees to freeze. The stuff at the top actually can keep getting colder until it creates ice along the top. And so it might actually do that. It might create ice along the top, and then I've got an ice barrier right up here along the top of my stream. Hey, anybody ever been in an igloo? Probably not. But anyway, igloos work because once you have ice over something, it actually traps the heat. And you're less likely to get the bottom of this to freeze. So the ice floats on the top, and it keeps the bottom part flowing. Which is why our streams do not kill everything in winter. It's also why our systems on Earth work in general, and why water might be the reason things live through the temperature changes that we have here on this planet. So water is pretty important for life. All right, one more of these little scenarios. To test blood sugar regularly, diabetics have to prick their finger, get the blood to enter a small machine where it can be measured. We only want to use a very small amount of blood, but are concerned that getting a few drops into the machine is difficult. What aspect of water might help us move the blood into the part of the machine that can measure the sugar? Okay, so we've been talking mostly at this point about water sticking to itself, which is an important thing. Water does stick to itself. When it sticks to itself, we call that adhesion, and adhesion is what allows most of these other things we've talked about. But it doesn't have to stick to itself. It can also stick to other things that are similar to it. Like, for instance, the sugar and the salt can both dissolve in it. But what if you had a solid substance like that? Could you get the water molecule to move along it? For instance, what happens when you put a drop of water on, like, a piece of paper or a paper towel or something like that? Well, generally what happens is that it's able to climb or move along that. So what do you do with this? Well, we want the water to do the same thing, to climb or to move. We call that property of water, it's a little different, cohesion. Cohesion is when water molecules stick to another thing. It says what type of material will be used to help with this process? Well, it needs to be something that sticks to water. Thing that, for instance, likes water so the water can climb it. Ooh, turns out we have a word for that. That word is hydro for water. Philic for liking. That's that word. There's another pretty similar word that we're going to get to in a second, only it means the reverse. So we want to use a type of material that would be hydrophilic. By the way, if you've ever seen them, where they put the little glass tube on your finger to pick up the blood, glass. It's hydrophilic. Water sticks to it. So that's how come they're able to do that with the teeny tiny tube. They can get it to climb right on up. Okay. I said one more thing, and it relates to those words. Hydrophilic and hydrophobic, phobia being fear of, in this case, staying away from water, like our oil and our cholesterol from the beginning. All right, so if you want to keep a small amount of salt water separated from a larger amount of fresh water. So let's imagine this. Maybe I'll make my salt water this kind of greenish stuff, and I'll make my fresh water this big bluish thing. And I want them to not mix together. Well, the problem is water mixes together. Salt mixes with water. So if I just leave them on their own, they're not going to work. They're going to come together and they're going to start to mix. So I need to put something in between them. And if I want them to not mix with the something, you know that something needs to be? It needs to be hydrophobic. So a hydrophobic barrier or a hydrophobic thing around the salt water would probably work. All right, similar but different. If I have an amount of water and it's hanging out, for example, in my space, oops, gotta change the color, that's not water. Have an amount of water and it's hanging out in my space, like on my table or something, what's gonna happen? Usually it seeps, it spreads, it gets somewhere. I certainly can't contain it. Unless I put it in something. So what am I gonna do? Well, I'm gonna try to put it in some kind of container. And again, if I don't want it to mess with the container or mix with it or fall out of it, I need my container to be, same as before, hydrophobic. Hey, remember a moment ago we were also talking about cholesterol and said maybe it's also used kind of in structures? Guess what hydrophobic things are good for? Hey, keeping things separated from water, like structurally. Hey, wait a second, what are you mostly made of? I feel like you're made of a lot of water. You are made of a lot of water, but you are not a puddle on the floor. How come you're not a puddle on the floor? Why am I not a puddle if I'm made of mostly water? Guess what? I'm also made of fat. Hydrophobic materials that keep the water contained inside of me so that I can work with both of those. And that's how chemical structures are important to chemical properties, so we know how they work together and why we need to know about those things to build biology like us. So I have to understand the chemicals that make up me to understand how I'm put together. And I hope that was interesting to you. Thanks.